when we talk about circles and parabolas, and actually there's ellipses and hyperbolas that you have to include here, what we're really talking about are something called conic sections. And we're only going to talk about circles and parabolas. When you get to Math 13, you'll be looking at ellipses and hyperbolas as well. And where these shapes come from, we have these equations and you've drawn them out, and you can recognize certainly what a parabola is, and of course a circle, you've known what that is for a long time, but perhaps you don't know that these things come out of a conic section. And there's this big, long, three-dimensional equation in x, y, and z that establishes these cones. Okay, and so this cone is actually two cones. They meet at the vertex here. And it turns out that any equation that has a square in it, a second-degree equation in x and y, will graph to one of those purple shapes there. So we have a circle. If we take a slice through the cone, it'll be a circle. If we take a slice on an angle, we'll either have an ellipse, and you'll have the ellipse when this thing is stuck. Oh, well, I guess I didn't like it today. Well, anyway, the ellipse, you can see the ellipse. That's when you cut the cone at any arbitrary angle. But if you cut, okay, so if we just take this plane and take a slice through it at any particular angle, we'll get an ellipse. If we make the slice parallel to the side of the cone, we'll get a parabola. And if we do it perpendicular to the main axis of the cone, we'll get two hyperbolas. Or actually, it's a single hyperbola, but it has two lobes to it. And so it's kind of a nice analytical exercise to go through and transform a circle to an ellipse and all this kind of stuff. But we're not going to worry so much about that, so long as you just envision that when we're talking about conic sections, we're talking about equations in x and y where we have a degree of 2 in either the x or the y, or both. Now, circles. You did the worksheet yesterday, so a circle, you can look at it as you take the middle of the circle and you have the same distance in every direction, and you take the sum of all those points, and you get this round thing. And so since the distance from the side of the circle to the center of the circle is the same, you'd expect that the equation for a circle is going to look a whole lot like the distance formula. And in fact, it is the distance formula with x and y being a variable instead of a particular value. So it comes in two forms. One of them is the general form here. Actually, this is a standard form, but this is for a general circle, where we have this h and k, where h and k is the center. And remember, we use that as h and k as the vertex on a parabola. And so the h and k are associated with x and y in the same way that it was with a parabola. Those are the things that, remember, when we stick h and k in a function, we'll get a translation of a function, where we get f at x minus h plus k equals y, that kind of stuff. The h and the k are associated with the same letters. So if you have a hard time remembering, or if you get confused, or you see something turned around and you're not sure, is h always goes with x, k always goes with y, and just remember alphabetical order. H and k are in alphabetical order, x and y are in alphabetical order. So even when we're turning these things on the side and we're perhaps using a y squared instead of an x or whatever, we'll see this in parabolas where we're going to change the orientation of the parabola. K is always associated with y, h is always associated with x. And so when h and k are the origin, 0, 0, those drop out and you just get r squared equals x squared plus y squared. And so that's the simplest circle that you have. R squared is the radius. Okay, so let's look at this equation. Now, I didn't have any coefficients in the stuff that I gave you yesterday, but let me show you how you treat coefficients. The fact that these coefficients are the same, and we have an x and y squared, and it's the sum of those two, that tells you it's a circle. Now, if they were different, if this was, let's say, 7 and 5, we'd actually have an ellipse. Okay, so the first thing we're looking for when we're trying to decide if something's a circle is, are the coefficients to the squared terms the same? Here they are. So what we have to do is transform this into that, to the form that we've had before that tells us where the center is and what the radius is. And so we just basically do some manipulations, can divide both sides by 5, and so we get x squared plus y squared equals 4. So what's the radius here?
2.
2, right? It's an easy thing to remember once you get the equation. That's just, you know, an easy thing to forget that this thing is r squared, not just r. And so our radius is 2. Okay, so this equation represents a circle of a radius 2, and the center is at the origin because we don't have any h and k inside parentheses that are being squared. Okay, I'll do another example here. Now this one's a little bit more complicated. Here we have x squared plus y squared minus 10x plus 6y plus 25 equals 0. Maybe it doesn't jump out at you as a circle right away, but the big clue is that we have x squared plus y squared with 1 as the coefficients there. And then all this other stuff is a result of us moving the circle off the origin. And so the way we're going to find the, put it in standard form, is we'll put the constant on the right side and we'll group the x's and the y's, and now we'll complete the square 2 times. Okay, we'll complete the square for x and we'll complete the square for y. And so if I go through my factors on the first one, I have 2b equals negative 10. I have 2b equals negative 10, b equals negative 5, b squared equals 25. So on the x portion of this, I'm going to add and subtract 25. And then on the y portion, my 2b is 6, so b equals 3, b squared equals 9, so I'm going to add and subtract 9, and I'm leaving that negative 25 alone. And now I'll factor things. And so what I get is, I get x minus 5 squared. The negative 5 comes from the fact that my b was negative 5. The 3 comes from the fact that my b here was 3. I don't have to go through the pain of factoring these 3 terms. And then I still have the negative 25 and the negative 9 left over. So what I'm going to do is I'm going to put them at the end, and now I'm going to add 25 to both sides of the equation and add 9 to both sides of the equation, and I get now something that is very, hopefully very familiar. This is the equation of the circle in standard form. So we can read off everything we need to know here. So it's a circle with a radius of what? 3, right? And where's the center?
5.
Yeah, 5, negative 3. Now notice here, and this sometimes gets a little confusing. When I'm using this kind of method of completing the square, I'm taking the negative 5 right in with the same sign, and I'm taking this 3 in with the same sign. But when I look at my equation here, this is x minus h and x minus k, so we have to take that into account and get the h is 5 and the k is negative 3. So there's the center of the circle. So this thing translates around just like any other equation that we've been dealing with. Okay, so you had some exercises on circles. I'm just going to move ahead there. We're not going to try any in class necessarily. Now parabolas, we've dealt a lot with parabolas, right? We went through the whole thing with quadratic equations. We've completed the square. We found the vertex, axis of symmetry, intercepts, and all that. There's one other aspect of it that we haven't talked about, and this, in a lot of respects, is one of the most interesting things about a parabola. There are two other places, or two other things that are important with a parabola. One of them is the focus, and the other one is something called the directrix. Now, the focus is literally where the parabola comes to the focus. Okay, when they were inventing telescopes, Galileo with his refracting telescope, that was pretty successful. He discovered the moons of Jupiter with them, but Sir Isaac Newton was probably one of the most brilliant minds of all times, right? And he was one of the inventors of calculus, and he did a lot with math, and he found that he did a lot with these kinds of things, and he was aware that this thing we call the focus is there. And what the focus and the directrix, where that comes into play, is that if you take any point on the parabola and measure the distance between that point on the parabola and the focus, that'll be the same distance from that point on the parabola down to the directrix. So the consequence that this has for the telescope, forget about the directrix. If you make this a mirror, the light's going to go straight up here, and so any point that leaves the focus and hits the parabola goes straight out as a parallel line. And if you play that backwards, if you let light come in like that, you're focusing an image at the focus. And that's exactly the sense that we think of the focus, right? You take a glass and you focus it, or camera, you focus it. A Newtonian telescope works this way. It takes a parabolic mirror, not a real deep one like this. They usually use just the very, very shallow part of the parabola, and so you get an image projected, and then if you use it with the right eyepiece, you get a magnification. So this is one of those things. It's a physical situation that causes a parabola. It's not just an equation that we invented and we see what the graph looks like. Here is a definition for a parabola that leads to a shape. So there again, if I take any other point, perhaps my drawing isn't exactly to scale, but if I take this point on this side, it's going to be an equal distance from there to the focus and from there to the directrix. Okay, so that's essentially what I've said with all those words in fewer words. All right, so let's say we need an equation now to describe this. And what has been found over the years is that if we say x squared equals 4py, that p is the distance from the focus to the vertex. Okay, so this equation, x squared equals 4py, p is the distance from the focus to the vertex. Okay, so we know we can find the vertex, and all we have to do to find the focus is to put the equation in this form and calculate what this p is. Now, a parabola can either go up like this or it can go down like that. And so normally we've been talking about distances as being always a positive number, right? But here we're going to make a distinction between a positive number where the focus is above the vertex, or a negative number where the focus is below, and then we'd end up with a vertex like that. So make sure you pay attention to the sign of p. Now the other thing about the directrix then is it's the line that has the same distance p from the vertex down to this line. And normally we're not too concerned about finding the equation of the directrix. The directrix is there as kind of a virtual plane that actually makes these parallel lines work in our mirrors and things like that. So, okay, so let's go over an example here. The basic parabola, right? Okay, so in our basic stripped down, no numbers other than the squared in there, where is the directrix on this? Okay, so what we do, not the directrix, where's the focus? So we look at this, the coefficient, and we say the coefficient is 1, right? It's definitely not 0, it's 1. And so we know that this expression here that's in front of the y should be 4p, and in this case it equals 1, so p equals 1/4. So when we have our graph, we know that the focus is going to be at 0, 1/4, and that the directrix is going to be at y equals minus 1/4. Was that too fast? Are you still taking some notes? Yeah, I'll go back. Okay, so let me do a couple more examples. So what I want to do is I want to find the equation of a parabola with the vertex at 0, 0 and the focus at 0, 2. Okay, so I know my p-value is going to be, let me see, the focus is below the vertex, so the p is negative, right? When the focus is below the vertex, p is negative. And so this is the form I'm looking for, and I know, and that 4 is just an artifact of the way this thing was derived, so that's always there. And I know my p, from looking at those 2 points, is going to be negative 2, so my equation, when I simplify it out, is going to be negative 8y equals x squared. And so that's what we call in standard form. Now we're not used to seeing it that way, right? We usually write a parabola as y equals some expression. And so if I divide both sides by negative 8, I'll get y equals negative 1/8 x squared. Okay, so that's when we're given the focus and vertex, we can get to the equation. Okay, we'll do another example here. Oh. Before we do the example, we have the same thing going on with h and k that we had with circles and with all of our translations, where instead of just y, we'll take y minus k in parentheses, and instead of just x, we'll take x minus h in parentheses. And so here we can use this. We'll know where the vertex is, because that's h and k, so we'll have those two values. And we know that the p is the distance from the focus to the vertex. So here's the example that I want to use now. Find a parabola with the vertex at negative 1, 2, and the focus at negative 1, 0. Okay, so let's try and envision this. So the vertex is at negative 1, 2. All right, so that's, you know, in your mind's eye, perhaps you can see this. It's going to be right here. The focus is going to be at, so we'll call this V for the vertex. The focus is going to be at negative 1 and 0. I'll put an F for that. So what's the value of P going to be here? Anybody?
It would be a negative because of running down.
Yeah, and then what's the value of it? Negative what?
1/4.
No. Just P. Ignore the 4 in the equation. I just want P. P is the distance from here to there. And we established, since this is the focus is below the vertex, it's going to be negative, so it's negative 2. Okay? And so we just pop those numbers into our equation. P equals negative 2. So when we put those numbers in and simplify, there's the standard form of our equation. So just like we had this is this, we had the, well, we have a lot of different forms for parabolas, right? And so if we want to put it into general form, then we just expand the squares and then collect all the terms and divide by the coefficient of y. And so we get this equation here. And this is just nothing more than expanding the x plus 1 squared and then putting it all on one side, having y on this side with no coefficient, and then everything else on this side. So first thing we do is we subtract 16 from both sides, and then we divide both sides by -8, and so it turns out that this is our equation here. Now notice when I had integers for my vertex and focus, I get these weird fractions for the general form. And that's kind of the way it is. You know, if we have integers for these distances, we're probably going to end up with fractions. If we have nice integer coefficients in our general form, we could end up with a fractional location for the focus. And that's just the way it works. Okay, the wider the parabola, the longer the distance that we have. Now this also works for horizontal parabolas. And so what I showed you here and what we've talked about so far is just 4py equals x squared. If we swapped x and y, so it's 4px equals y squared, we're going to get a parabola that is like this. Now this is for a positive p, and this is for a positive p as well. The focus is down the x-axis here. So here the focus is further from the origin, so we have a positive p. And then if we want to put these with the displaced version, you know, what we had before was 4p equals y minus k equals x minus h squared. And then the horizontal version of that would be 4p times x minus h, y minus k squared. So how do you tell which one is which? You can tell the difference if you're given the vertex by where the vertex lies with respect, where the focus lies with respect to the vertex. Okay, everybody up with me? I'm going to try and round this out before the end of class here. Okay, so what I want to do is I want to find a parabola with a vertex at -2, 1 and the focus at -4, 1. So let's envision this first. So the vertex is going to be at -2, 1. That's right there. And the focus is going to be at -4, 1. Right there. So here's the focus, there's the vertex. Now this is going to be the version that has y squared, not x squared, because it's going to go like this, right? And we know that p, since the focus is a smaller number than it's to the left of the vertex, that's going to be, the p is going to be negative. And so for the solution, okay, since the focus is to the left, you'd expect a negative p. And so we're going to use the form of the equation that has the y in the squared term, because that gives us the horizontal orientation. And so we'll just substitute in our values. First calculate what p is, that's a -2, and then pop in the vertex values for h and k, and then when we simplify that we get this equation here. Now it's not a function, obviously. Not every equation is a function. When you have a parabola leaning over on its side, any given x, there's 2 values of y, so it's certainly not a function. Okay, I think we're going to stop here, okay? There's a way to translate the